Hello. Hello. Hi everyone. Can you hear me? Hello. Can you guys hear me? Okay, let's get started. Uh, yeah, so this is week six, so we'll look back at previous year's week six questions. The first question reads: which one of the following is incorrect about biofilms on implant surfaces? It prevents antibody penetration to the bacterial surface. It sequesters bacteria specific ions and nutrients. It increases antibiotic interaction. It enhances virulence of the bacteria, or it prevents macrophage bacteria interactions. What do you guys think could be the correct answer? Which one of the following is incorrect about biofilms on implant surfaces? It prevent antibody penetration to the bacterial surface? Is that an incorrect statement to make? Or does it sequester bacteria specific ions and nutrients? Does it increase antibiotic interaction? Does it enhance virulence of the bacteria? Or does it prevent macrophage bacteria interactions? Any idea? So they're asking for an incorrect statement about biofilms on implant surfaces. So which one of the following statements is false? Prevents antibody penetration to bacterial surface, sequesters bacteria-specific ions and nutrients, increases antibiotic interaction, enhances virulence of the bacteria, or prevents macrophage bacteria interactions. You guys can type the answer if you are not, or if you do not have access to my mail check. Come on, guys, type an answer. What do you guys think happens in a biofilm? Does it prevent antibody penetration to the bacterial surface? Or does it sequester bacteria specific ions and nutrients? Or does it increase antibiotic interaction, enhance virulence of the bacteria, or prevent macrophage bacteria interactions? Sorry, which one?
It increases antibiotic interaction.
Yeah. So that would be the false statement, right? So if anything, it decreases the antibiotic interaction. Why? Because biofilms are these. So if you have an implant, and if there's a biofilm growing on top of it, it's a very thick wall of extracellular. There's bacteria present on the implant and within the biofilm, but this biofilm is made up of extracellular matrix. A lot of protein, lot of cellulose, lot of DNA, RNA, so on and so forth. So it prevents things from going in and reaching the bacteria that's present within the biofilm as well as on the implant. So it increases antibiotic interaction is an incorrect statement. Yeah, so that's the false statement. Okay, moving on. Why are stents used in blood vessels for tissue engineering? Two options are correct here. Are stents used to heal blood vessels? Are they used to prevent hemorrhage? Are they used to open occlusions from the blood vessels? Are they used to bypass a blocked artery or vein? Do they help grow a new blood vessel in its vicinity? Does it help prevent senescence? Senescence meaning basically the cells stop dividing and multiplying. To cause further, do they cause further damage to excessive blood vessels, or do they increase the diameter of blocked blood vessel, hence increasing fluid flow? Why are stents used?
It's option 3 and the last one.
So to open occlusions from vessels and to increase diameter of blocked blood vessel, hence increasing fluid flow. Yeah, correct. So stents are basically insertions in the blood vessel where they sort of there's a balloon as well in the stent. So once you blow the balloon, they expand and increase the diameter of the blocked blood vessel. So there is more flow from the through the blood vessel, but at the same time they can also help clear occlusions from the vessel. So there's also a vacuum pump attached to it where you can start sucking out things. Okay. Which of the following methods would you use to prevent bacterial adherence on device? Pick two options. Rough surface, regular smooth surface, hydrophilic surface, or hydrophobic surface? How would you prevent bacterial adherence on a surface? Does the surface have to be rough, regular smooth surface, hydrophilic surface, or hydrophobic surface? Think in terms of the surface area of the surface, uh, how the surface area would change with it being regular or smooth, as well as what the bacterial cell wall is made up of.
Hydrophilic surface.
Yeah, hydrophilic surface because the bacterial cell walls are generally hydrophobic, so they like to stick together. Two bacteria would like to stick together, and they would also like to stick to other hydrophobic surfaces. So if you want to prevent bacterial adherence, you will make your surface hydrophilic, so they are less likely to stick together. Now, amongst the smooth and rough surface, which one do you guys
Smooth.
think? Yeah,
Smooth.
smooth.
Regular
Regular
smooth.
smooth surface.
Yeah, so a regular smooth surface will have less surface area compared to a rough surface, right? So rough surface has all these grooves and dips, and that increases the surface area compared to a regular smooth surface. Yeah, so regular smooth surfaces and hydrophilic surfaces prevent bacterial adherence to devices or surfaces. Okay, moving on. Which implant device has the highest rate of infection? Pick one option. Dental implants, vascular grafts, mammary implants, penile implants, heart assist valves, or fracture fixation devices. What do you guys think? Which of the following has the
Heart assist devices.
okay?
Heart assist devices.
Okay. Any reason why you think heart assist devices would have a higher rate of infection? You're correct. So, heart assisted devices will have the highest rate of infection. But why? Think in terms of how much of your uh, body weight or percentage each device is coming into contact with, right? So if it's a heart assist device, heart is pumping blood, and you have about 6 liters of blood in your body. So pumping all that blood, and if there is infection that has entered into your bloodstream, either through the insides of your body or the outsides of your body, it's going to get your heart is going to get exposed to that infection, and as a result, heart assisted devices will also get exposed to that infection. So, heart assist devices will have the highest rate of infection. Okay, moving on. What are the common approaches used to reduce implant associated infections? So, two options are correct here. How would you reduce implant associated infection? Do you reduce them through sterilization, gene bombardment, surface modification, coating with a metallic paint, annealing, heat working, or pulling into sheets?
Surface modification.
Yeah, surface modification and yeah, sterilization as well. So you go for sterilization wherever possible through whatever possible means that are available, and you do surface modifications like we previously discussed, right? So making the surface more hydrophilic, so on and so forth. So yeah, so those two techniques you can use to reduce implant associated infections. Okay. Which one of the following is not a feature of implant infection? This is the next question, right? Yeah. Which of the following is not a feature of implant infection? adhesive bacterial colonization on the material, resistance to host defense mechanisms and antibiotics, transformation of non-pathogens or opportunistic to virulent organisms because of the presence of biomaterial substratum, persistence of infection until removal of the material, absence of tissue integration, tissue healing, presence of tissue cell damage and necrosis. So they're asking which of the following is not a feature of implant infection. So infection has already happened and the implant is infected. So yeah, so tissue healing is definitely not a feature of implant associated infections, right? So, if anything, there will be tissue damage and necrosis. Tissue healing is where the implant associated infection is dissolved and there's a chance for your tissue to regenerate. Okay. So, how biofilms inhibit host defense mechanisms? Pick the false statement. So, how do biofilms inhibit host defense mechanisms? Do they prevent antibody penetration to the bacterial surface? Uh, do they reduce virulence of the bacteria in biofilms and make them more susceptible to immune effectors? Do they prevent macrophage bacteria interactions? Do they reduce polymorphonuclear leukocytes like neutrophils to move into this location through chemotaxis? Do they enhance virulence of the bacteria or do they prevent antibiotic interaction? So, how do biofilms inhibit host defense mechanisms? What is the false statement? Some of these are true, uh, most of these are true, only one statement is false. We've previously discussed the first point, right? So, preventing antibody penetration to the bacterial surface. So, is that true or false? Do biofilms prevent antibodies
It's
from?
true.
Yeah.
True.
So, yeah. So, biofilms again are made up of extracellular matrices. So, they prevent antibodies from penetrating and reaching the bacterial surface. Do they reduce virulence of the bacteria in biofilms and make them more susceptible to immune effectors, or do they enhance the virulence of the bacteria? What do you guys think?
Enhance the virulence of the bacteria.
Yeah, so biofilms generally enhance the virulence of the bacteria. So they do not reduce the virulence of the bacteria in biofilms. If anything, they make them more virulent. And they do not definitely make them more susceptible to immune effectors, right? So immune effectors in the first place are not able to reach the bacteria. Okay, so this seems like a false statement. Do they prevent macrophage bacteria interactions?
True.
Yeah, so if antibodies cannot get through the extracellular matrix, there is no chance macrophage is going through the extracellular matrix. Uh, do they reduce polymorphonuclear leukocyte chemotaxis? Same thing
Yes,
as
sir.
this, right? So no cell is going to go into the biofilm so easily. And do they enhance? Yeah, so we've discussed this. They do enhance the virulence of the bacteria. Do they prevent antibiotic interaction? Do they prevent antibiotics also from reaching the bacteria? They do. So not all antibiotics. Some antibiotics can still reach, but to the most part, biofilms are big. So and they keep growing. So the amount of antibiotic that's present at the core of the biofilm is often very less compared to what's present at the periphery of the biofilm. So they do prevent antibiotic interactions with and bacteria in biofilms are generally at the core. So yeah, so reducing virulence of the bacteria in biofilms and making them more susceptible to immune effectors is a false statement. The opposite happens. They increase the virulence of the bacteria in biofilms and they make them less susceptible to immune effectors. Okay. Which of the following is an advantage of a decellularized matrix? So two options are correct here. Toxicity of the detergents used is an advantage. Fragments of ECM triggers clotting cascade in the body, which could be an advantage. Matrix does not trigger immune response. The network of natural ECM is suitable for growing cells, and they are difficult to produce on a large scale, therefore being an advantage. What do you guys think?
So third and fourth, the matrix does not trigger immune response as
Y-
it is from the natural.
Yeah. So yeah, generally a decellularized matrix does not contain any cells. It just contains the extracellular matrix, right? So the cytoskeleton, the extracellular skeleton, and the extracellular matrix. So the matrix does not trigger immune response because there are no cells, no proteins, so on and so forth. And the network of the natural ECM is suitable for cell growth because cell growth was already happening there. So in that way, it's architecturally very suitable for cell growth. Yeah. So those two options are correct. Okay. Which of the following is not an objective behind tissue engineering? To generate neo tissues to replace damaged tissue, to generate tissue in vitro which can be used to regenerate damaged tissue, embed cells like neutrophils and macrophages in scaffolds to enhance inflammatory profile of the damaged tissue, to add support or filler material to help the function of tissue, putting scaffolds to help regenerate damaged tissue, or embed cytokines like interleukin 1 beta or MMPs like matrix metalloproteinase 13 to create more damage to the tissue. So, which of the following is not an objective of tissue engineering?
The third one,
Third one, so you don't want to embed cells like neutrophils and macrophages. Why?
as it is always is present in our body,
Yeah,
it will
so they will trigger a very strong inflammatory profile, right? So if you take a new material, put neutrophils or macrophages in it, either patient derived or derived from species, what ends up happening is once in the body, they'll start triggering inflammatory profiles and set up an inflammation cascade. Yeah, you are correct. So that's not an objective. What is the other one?
last one, the embedding cytokine like interleukin
Yeah.
1 beta and matrix met- metalloproteinase 13 to create more damage to the tissue.
Correct. Yeah. So you don't want to create more damage to the tissue. And if you look at these cytokines, interleukin 1 beta will is a pro-inflammatory cytokine, so it will again cause inflammation. Matrix metalloproteinase 13, like most MMPs, are basically proteins that can cleave extracellular matrix, right? And they can create more damage. So you don't want to do that. Yeah, so those two are definitely not objectives of tissue engineering. Okay, last question. So consider that insulin releasing cells are embedded in a scaffold made of collagen. The release rate from the scaffold is given by the equation R2 is equal to 2.2 moles per second. The dimensions of the scaffold are as follows. Area is 25 millimeters squared, width is 2 millimeters. Now, what they're asking is in steady state, how much insulin will be released in 5 seconds? Report your answer in millimoles. You can solve this question. Fairly straightforward. You have everything you need to solve the question given. So, tell me the answer. So, they've given you few things. They've given you the release rate and they've given you the dimensions. And they're asking in steady state how much insulin will be released in X amount of time, in this case 5 seconds.
Sir, I have doubt in solving this question
Yeah,
because,
go on. What's your doubt?
like, if it is rate is 2.2 millimolar per second and the area is 25 millimeter per square and width is 2 millimeter,
Yeah.
then how can we find,
How can you match?
like what formula we used?
Ah,
Can
okay. Yeah, we'll discuss. Yeah. So does anyone else have any doubt, or else I can discuss the question. Okay. So fairly straightforward. So what they've given you is the release rate. That is all you need really. They gave you area and width to confuse you. This is not the information that you need. It doesn't matter because you know the release rate of this.
sir 2.2 into 5,
Yeah,
2.2 into
exactly.
5.
So you know how much of insulin is getting released per second, right? You know 2.2 millimolars of insulin is getting released every second from this device. They are simply asking you how much will be released in 5 seconds. So 2.2 into 5. 2.2 into 5. That will be what? 11, right? 11 millimoles. That's it.
Thank you, sir.
Yeah. Any other questions? Do you guys have any other doubts or questions that you want to discuss? How's the course going so far?
That's going well.
Do you find it easy, hard, or challenging?
On the uh,
Sorry?
moderate.
Moderate. Okay, good. That's good. So, yeah, so if you guys have any other questions, we can discuss now. But otherwise, we don't have anything else to discuss this week. So, you can leave.
Sir, one more time, if you discuss the biofilm, how biofilm role in antibiotic and other drugs inside our body.
Sorry, I could not hear you properly. Your voice is getting cut. Can you repeat the question again?
So my question is how the role of biofilm in immune response.
Ah, okay. So,
Like,
yeah, okay, we'll talk about this. Okay. So, do you know when biofilms are formed?
sir, when there is when you put any implant in our body, then there is competition between protein and bacteria, and there is a layer formed due to the bacteria's adsorption on the surface.
Yeah.
And this bacterial adsorption in the surface creates a layer that layer prevents that layer particular act as
Yeah, so you're correct. So there is adsorption of bacteria onto the surface of the biofilms on the of the implant. So in this case, this is the implant, and these are the bacteria that are getting adsorbed onto the surface. Now, these conditions are not favorable to the bacteria, at least in the body, right? Because an outside bacteria, what will happen is your macrophages will come and start eating them up. So yeah, so your macrophage will start coming and eating them up and cutting them into pieces, killing them and presenting them through major histocompatibility, complex proteins, and generating an immune response. So the bacteria is sort of sticking onto this implant, and now what happens is the bacteria is, because it's in the body, it's under a stress condition, and it has an anchor point here. So, and most bacteria, they have this unique characteristic. Whenever they have an anchor point, what they'll do is they'll start secreting a lot of proteins, right? So they'll start producing a lot of proteins. They'll start producing a lot of lipids, uh, polysaccharides, lipids, proteins, so on and so forth. And some bacteria is going to die, so they'll release out their DNA and so on and so forth. So all of this will form this very thick layer around the bacteria, and this is now covering your, because the bacteria is on the implant, it's covering your implant. So it might not happen throughout your implant. So if this entire thing is your implant, if there is bacteria here, so it could just be biofilm here. Now, what happens is over a period of time, the bacteria inside the biofilm. Now, this biofilm is basically, like I've told you, it's made up of proteins, polysaccharides, lipids, so on and so forth, DNA, RNA, and others, right? So, all bacterial components, bacterial proteins, bacterial polysaccharides, so on and so forth. Now, what happens is, because they're forming such a thick mass, there is so nutrition like glucose, right? So glucose, or other nutrients like amino acids, all of this will have, so the way they reach different areas in your body is through diffusion. Now, because there is this thick mass, these are going to be limited, so their penetration is sort of prevented, and this puts bacteria in a more stressful condition. So what they'll do is they, some of them will enter this non-replicating state. Some of them they'll start replicating and producing several other factors, and so on and so forth. So the bacteria is in a very stressful condition. So it will produce more biofilm, and it will start putting itself in more and more biofilm. So the biofilm grows over a period of time, right? So basically this thick extracellular component of proteins, polysaccharides, and so on and so forth, they grow. And what happens is proteins they stick together, and polysaccharides they also come together. So all of this they'll form like a very sticky film, and this sticky film, now if something, so like I've said, nutrition is also not properly going in, but if you deliver antibiotics or something else, what happens is, because they're this thick film, they are also not able to diffuse through the film very easily and reach the bacteria, so their diffusal rate is also severely limited. Does that answer your question?
Yes, sir. My doubt was how this bacteria is creating virulence, not creating virulence. And, like we are expecting that bacteria
Yeah.
is inside
Okay.
inside in
Y-
biofilm bacteria is there, but we are using it in a clinical trial or anything. So how this biofilm is not creating any virulence?
Yeah. So
Any,
biofilms can create virulence. But that typically happens when the virulence factor is because of a bacterial produced protein, right? So, for instance, if you have a tetanus bacteria, so the tetanus bacteria by itself is not dangerous to humans. It produces a toxin called the tetanoid toxin protein. So it's a protein. So that protein is what is dangerous to humans. And if there is a tetanus bacterial biofilm that's made up of a percentage of tetanoid protein, then that's going to be virulent to humans. It's going to be toxic and virulent to humans. So it depends on the type of bacteria that's forming the biofilm. So not all biofilms necessarily can be virulent, but it does not mean that biofilms are not virulent. They can also cause inflammation. They can also cause severe immune reactions, so on and so forth.
Thank you, sir.
Yeah. Okay. If you guys have no other questions, then we can stop here. Uh, yeah. See you guys next week. Bye. So jumping into the question, so the first question reads, which one of the following is incorrect about biofilms on implant surfaces? It prevents antibody penetration to the bacterial surface. It sequesters bacteria-specific ions and nutrients. It increases antibiotic interaction. It enhances virulence of the bacteria. It prevents macrophage bacterial interactions. So, which of the following statements would be incorrect about biofilms? What do you guys understand about biofilms? Is it a host response, meaning humans are producing these biofilms, or is it a pathogenic response, or is it the biomaterial itself that's producing these biofilms? Who is producing these biofilms?
Biometal itself, sir.
Okay, so usually these biofilms are produced by the pathogenic bacteria. The bacteria are what produce these biofilms in response to environmental stresses, be it antibiotic treatment, nutrient deprivation, immune stress, so on and so forth. So there can be so many different reasons why bacteria can produce these biofilms. And this is a big problem for implants and such because the implants, the very interface of implant in the body attracts a lot of immune cells, and if you have antibiotics in your implant, they'll slowly be released at the interface of implant and the body, and bacteria which can produce biofilms. Like, does anyone know what the most common biofilm producing pathogenic bacteria is in humans when it comes to implants? There are a couple, but have you guys heard about Pseudomonas aeruginosa and Staphylococcus aureus? So Pseudomonas aeruginosa is one of the bacteria that has this great potency to produce biofilms. So, and it's a major clinical problem. So, a lot of patients with these implants, they come with Pseudomonas aeruginosa infections. They would usually have these biofilms. So now the question is, which of the following statements is incorrect about these biofilms? Do they prevent antibody penetration, or they sequester bacteria-specific ions and nutrients, or do they increase antibiotic interaction, or do they enhance virulence of the bacteria, or do they prevent macrophage bacteria interactions?
The following is incorrect about
So the way to think about it is biofilm is being produced by the bacteria, and the bacteria produces biofilm in an attempt to survive harsh environmental conditions, right? Be it antibiotics or immune system. So if a bacteria is producing this biofilm to survive antibiotic rich environment, would it increase the antibiotic interaction or decrease the antibiotic interaction?
decrease the antibiotic interaction.
Correct. So then the incorrect option would,
That's it. That okay.
yeah.
It
So
increased.
the incorrect option would be it increases antibiotic interaction. So biofilm is nothing but a very rich extracellular matrix along with some slimy substance that the bacteria can produce. Okay, yeah. So it it in fact decreases antibiotic interaction. In fact, it prevents antibiotic as well as antibody penetration and interaction with the bacteria. Okay, moving on. So, why are stents used in blood vessels for tissue engineering? Two options are correct here: to heal blood vessels, to prevent hemorrhage, to open occlusions from blood vessels, to bypass a blocked artery or vein, to help grow a new blood vessel in its vicinity, to prevent senescence, to cause further damage to excessive blood vessels, or to increase diameter of blood vessel, hence increasing fluid flow. Wires.
Last option, sir, to increase diameter.
Okay. What could be the other option?
Third one, sir, to open oxidation from vessels.
Okay. Yeah, so basically, stents are used in case of occluded vessels, right? So, if you remember seeing a stent, so it's basically a surgical instrument that's pushed through the vessel, and there's a balloon which sort of blows up and enlarges this vessel. There is a mechanism to clear the occlusion, something like a vacuum pump, and the stent ultimately is the metallic or polymeric device which will hold the blood vessel in its increased diameter state. Okay. Which of the following methods would you use to prevent bacterial adherence on a device? Pick two options. Would you have a rough surface, a regular smooth surface, a hydrophilic surface, or a hydrophobic surface? How would
Following.
how would you prevent bacterial adherence on a device?
Regular smooth surface
Correct.
and
So would you want a hydrophilic surface or a hydrophobic surface? So when you're thinking about whether you want a hydrophilic surface or a hydrophobic surface, think about what interacts with the device, right? So in this case, what part of bacteria would interact with the device? It would be the cell wall. What is
yes,
this cell wall made up of?
cell
Lipids
wall,
and proteins.
polysaccharides and
Po-
lipids.
Polysaccharides, lipids, proteins, right? So
Yes,
And the lipids may be it is consist of head and tail and it is hydrophilic and hydrophobic.
correct, correct. So, if you look at the orientation of the lipids, okay. So in that case, what would the bacteria ideally prefer? Would it prefer a hydrophilic surface or a hydrophobic surface? If it's made up of
hydro,
this,
hydrophobic.
correct. So,
Answer is hydrophilic.
yeah. So it would prefer a hydrophobic surface. But if you want to prevent the bacterial adherence, you would want a hydrophilic surface then. So because the bacteria likes hydrophobic surface, you want a hydrophilic surface. And if you have a rough surface, the surface area is increasing a lot, and it can provide niches for the bacteria to grow. So then you would want a regular smooth surface. Okay. Which implant device has highest rate of infection? Pick one option. Dental implants, vascular grafts, mammary implants, penile implants, heart assist devices, fracture fixation devices.
Heart
Which,
assist device.
okay, any other thoughts?
So heart assist devices.
Okay, okay, yeah. So heart assist devices are usually the ones with highest rate of infection because they are not. very easily accessible for you to maintain hygiene, like the dental implants. And usually, you do not want any drugs also associated with them releasing very close to the heart, and a lot of blood goes to the heart, right? So that's where you would have the highest rate of infection. Okay. So, what are the common approaches used to reduce implant associated infections? Sterilization, gene bombardment, surface modification, coating with a metallic paint, annealing, heat working, and pulling into sheets. So, what are the common approaches used to reduce implant associated infections? Two options are correct here.
Sterilization
Yeah.
and surface modifications.
Okay. Yeah. So you can sterilize your implant, and you can also surface modify it with maybe peg to prevent bacterial adherence. So those are the two approaches that are commonly used to reduce implant associated infections. Okay, moving on. Which one of the following is not a feature of implant infection? Adhesive bacterial colonization on the material, resistance to host defense mechanisms and antibiotics, transformation of non-pathogenic or opportunistic to virulent organisms because of presence of biomaterial substratum, persistence of infection until removal of material, absent, absence of tissue integration, tissue healing, or presence of tissue cell damage and necrosis. Which of the following is not a feature of implant infection? What does not happen during implant infection?
Tissue healings.
Yeah, tissue healing does not happen during implant infection, whereas all the other things can happen. So, transformation of non-pathogenic or opportunistic to virulent organisms. I've given you example previously, Pseudomonas aeruginosa, which is usually opportunistic, but once host immune system deteriorates or the opportunity presents itself, such as a biomaterial substratum, it can transform into a pathogenic bacteria and so on and so forth. Okay. How biofilms inhibit host defense mechanisms? Pick the false statement. Preventing antibody penetration to the biomaterial surface, reducing virulence of the bacteria in biofilms and making them susceptible to immune effectors, preventing macrophage bacteria interactions, reducing polymorphonuclear leukocytes, chemotaxis, or enhancing virulence of the bacteria, or preventing antibiotic interaction. How do these biofilms inhibit host defense mechanisms? So we're talking about host defense mechanisms here. So preventing antibiotic interactions does not really play a role. So does it enhance virulence of the bacteria, a biofilm? So yes, so biofilms are found to increase the virulence of bacteria. So they make the bacteria become more virulent. So that's not going to inhibit your host defense mechanism. Uh, Reducing polymorphonuclear leukocyte chemotaxis, preventing macrophage bacterial interactions, reducing virulence of the bacteria in biofilms, or preventing antibody penetration to the bacterial surface. So those are the options we have left. Uh, yeah.
Second one, reducing virulence of.
Okay. So if a biofilm is reducing the virulence of bacteria and making them susceptible to immune effectors, it's not really inhibiting host defense mechanism, right? It's helping the host defense mechanism. And in fact, biofilms are found to enhance the virulence of bacteria. So that might not be the correct option. So what else would be could be the correct option? What How are biofilms preventing your immune system from killing the bacteria or removing the bacteria? Oh, sorry. So they're asking us to pick the false statement. So
False
you're
statement. That's why, yes.
Yeah, you're correct. So reducing virulence of bacteria in biofilms and making them susceptible to immune effectors is in fact false. So they do not do that, and even if they do that, it's enhancing your host defense mechanism. Yeah, you're correct. Okay. Which of the following is an advantage of decellularized matrix? Two options are correct here. Toxicity of detergents used is an advantage. Fragments of ECM triggers clotting cascade. The matrix does not trigger immune response. The network of natural ECM is suitable for growing cells. Difficult to produce on large scale. So, which of the following is an advantage of a decellularized matrix? So, what is a decellularized matrix? You basically take a tissue from either the host himself or somewhere else, and you remove all the cells and you preserve the cytoskeleton, right? So that's what a decellularized matrix is. Now, what be the advantage? Does it not trigger immune response, or uh, does it trigger clotting cascade, or is it the toxicity of the detergents that are used, or uh, is it the fact that the natural ACM is suitable for growing cells, or is it the difficulty of producing it on a large scale?
Uh, the network of natural ECM is susceptible for growing cells.
Yeah, it's very
First
suitable
one.
for growing cells. Yeah.
And difficult to produce on large scale.
Okay. So difficult to produce on large scale would be a disadvantage, right? Because if you cannot produce it on a large scale,
Yes.
yeah. So what would be the
Okay.
other advantage?
Mm,
Does the matrix trigger immune response if it's taken from the host himself or herself or a very closely related species,
Matrix does not trigger.
right? So,
Yes.
yeah, so the matrix does not trigger immune response for a decellularized matrix, and the network of natural ECM is also suitable for growing cells. So, those are the correct options. Okay, so the next question is which of the following is not an objective behind tissue engineering? Not an objective. Two options are correct here. Is it to generate new tissue to replace damaged tissue? Is it to generate tissue in vitro which can be used to regenerate damaged tissue? Is it to embed cells like neutrophils and macrophages in scaffolds to enhance the inflammatory profile of the damaged tissue? Is it to add support or filler material to help the function of tissue? Is it putting scaffolds to help regenerate damaged tissue? Or is it embedding cytokines like interleukin 1 beta or matrix metalloprotein proteinase 13 to create more damage to the tissue? What is not an objective of tissue engineering?
The last one, embedding cytokines like interleukin will be.
Correct. So that would not be an objective because you're basically damaging the tissue more. What would be the other option?
And another one is embedding cells like neutrophils and macrophages
Correct,
to
correct. So
enhance the inflammatory profile.
yeah, you do not want to do that, right? So in fact, you want to do the opposite of both of these goals. So yeah. Okay. So the next question reads: Consider that insulin releasing cells are embedded in a scaffold made of collagen. The rate of release from scaffold is given by the equation R2 R squared is equal to 2.2 millimolar per second. The dimensions of the scaffold are as follows. Area is 25 millimeter squared and width is 2 millimeter. In steady state, how much insulin will be released in 5 seconds? Report answer in millimoles. Do we know how to calculate this?
Answer is 11, sir. It is a direct multiplication.
Correct, correct. So essentially, the information that they're giving you here is kind of pointless, the area and the width, because they've already given you the rate of release from the scaffold, which is 2.2 millimoles per second. Now, if 2.2 millimoles is getting released in 1 second, how much will be released in 5 seconds? So that would be 5 into 2.2, which is 11 millimoles in 5 seconds. Okay, so I think we are at